In this section, we'll talk about the Fundamental Theorem of Calculus. Now this sounds pretty big, and yes it is. The discovery of the Fundamental Theorem of Calculus was the one that basically made calculus an actual subject in mathematics. What we're going to do is connect the indefinite integral with the definite integral, and it turns out to be a pretty simple formula. We're not going to prove it, but the Fundamental Theorem of Calculus. Now you can do a little bit more than just this, but I'll just say as long as the function's continuous on the closed interval, and we've got the antiderivative that doesn't have a constant term, we deliberately avoid the constant term, then it turns out that the definite integral is just simply take the antiderivative, plug in b, plug in a, and subtract. So if you can take an indefinite integral, you could take a definite integral and calculate the numbers quickly and easily. I said no constant term. That's because when you subtract, the constant terms actually cancel out, so there's no reason to include them. And we do not do a plus c with our final answer, we just get a number. Definite integral, we get a number. For indefinite integrals, we get a plus c. I'll show you an evaluation notation method. This is the idea. When you calculate the antiderivative, remove your integral symbol in dx. Remember, they're always paired together. And then you're going to either do a plus c if it's an indefinite integral, or you're going to do the evaluation notation if it's a definite integral. In either case, you're never done. You need to either add the plus c or do the evaluation, but always take away the integral sign as soon as you've actually done the antiderivative. Let's do an example. Let's find the area under the curve x cubed plus x on the interval from 0 to 2. So I've already got it graphed here. What I want to do is show you a little picture. We've got the area under the curve. That area, if you recall, is represented by the definite integral, which would be on 0 to 2. 0 to 2 are my bounds. I'm going to integrate the function x cubed plus x with respect to x. This is the setup. We've got a definite integral. The definite integral, by the Fundamental Theorem of Calculus, we need to go back to 4.1 with the techniques we learned there. And remember the power rule. X cubed, I'm going to raise the power by 1 and divide by the new power. Same thing with x. X has a power 1, so I'm going to raise the power by 1 and divide by the new power. Just use the power rule like we did before. I just integrated. And so what we're going to do next is use this notation, 0 to 2, from a bracket. You don't necessarily have to use a bracket. Sometimes you use a vertical line. But either way, what this means is I'm going to evaluate this at 2 and at 0. The Fundamental Theorem of Calculus says that. Take the antiderivative, plug in 2, plug in 0, and subtract. Let's write this down. So I get 2 to the 4th over 4 plus 2 squared over 2, I'm just plugging in 2, minus 0 to the 4th over 4 plus 0 squared over 2. So I plugged in 2, I'm subtracting, and then I plugged in 0. Now I put parentheses there. The parentheses matter more than they appear in this problem. In this problem, you could get by without the parentheses because this is all 0, but in general, put parentheses around it when you're going, especially if you have 2 or more terms. Then it's incorrect if you don't use them. 2 to the 4th is 16. 16 divided by 4 is 4. 2 squared is 4, and 4 divided by 2 is 2. All of this is 0. So I get that the area under the curve is 6. That is a lot easier than doing a Riemann sum. Just 6. Let's do a couple more examples. We've got x squared minus 1 evaluated from 1 to 3. So again, the integrals just simply means use the power rule or whatever other rules you have. I've got x cubed over 3. Add 1 to the power, divide by the new power. And the integral of 1 is just x, evaluated from 1 to 3. So again, parentheses are very important. I get 3 cubed over 3 minus 3. Minus goes in the middle. 1 cubed over 3 minus 1. I get 27 over 3 is 9. Minus 1/3 minus 1. So here I get 6 minus 1/3 plus 1. I distributed my negative sign there. So this is probably easier to work with. I get 7 minus 1/3, which is 20 over 3 as my final answer. Next one, cosine x. If you recall, the idea is whose function has derivative cosine x? You might know the rule already, but you also know that the derivative of sine x is cosine x. So in particular, well, the integral of cosine x is sine x, evaluated from 0 to pi over 4. So we get the sine of pi over 4 minus the sine of 0. Sine of pi over 4 is square root of 2 over 2. Sine of 0 is 0, so I get square root of 2 over 2. Next example. Remember the strategy that we need to use whenever we have a quotient is we need to split it. Whenever I rewrite this, again, when I rewrite, I still use the integral symbol. I have not integrated yet. I'm going to do x cubed over x cubed plus 3x over x cubed dx. Simplifying that one more step, I get the integral from 1 to 2 of 1 plus, I'm going to write this as 3x to the negative 2. Remember, when you use the power rule, you need to get it as a power. So let me just say, well, x to the 1 over x cubed, if I subtract 1 minus 3, I get negative 2. Now I integrate. Integral of 1 is x. Got a 3 here. Integral of x to the negative 2 is negative 2 plus 1. Think about that. Negative 2 plus 1 is negative 1 divided by the new power. That's evaluated from 1 to 2. This is x minus 3 over x. Still evaluated from 1 to 2. The x to the negative 1 can move to the denominator. The 3 can become negative, and this is easier to do. So I get 2 minus 3 halves minus 1 minus 3 over 1. So I get 1 half minus negative 2. So I get 1 half plus 2 is 5 halves. Again, it's just a matter of take the antiderivative, take the integral if you will, and plug in the numbers, 2 and 1. Simplify to get your answer. Now, D has a star here, so feel free to stop and give this one a try, and then we'll come back to it. Hopefully you've taken a look at that problem. Let's go over it. The integral of x cubed is x to the 4th over 4. Integral of x is x squared over 2. And the integral of 3 is 3x. We're evaluating that from negative 2 to 2. So let's plug it all in. I get 2 to the 4th over 4 plus 2 squared over 2 minus 3 times 2 minus negative 2 to the 4th over 4 plus negative 2 squared over 2 minus 3 times negative 2. 2 to the 4th is 16. 16 divided by 4 is 4. 2 squared is 4. Divided by 2 is 2. And 3 times 2 is 6. Alright, I get the same answer for these two. Because negative 2 to an even power is still negative. And then this time I get a plus 6. So this turns out to be 0. This turns out to be 12. So my final answer is negative 12. Hopefully you guys did okay on that one. This next example is another star problem. So feel free to pause this video, give it a try, and see what you get. Okay, let's see how you did. The first step is, again, calculate the integral. The integral of e to the x is just e to the x. And we're going to evaluate that from 0 to 2. So this one's actually pretty straightforward. You'll get e to the 2 minus e to the 0. And so you just have e squared minus e to the 0 is 1. And I'm just going to call that a quick final answer. Hopefully you did okay on that one. Let's do the next one. This one has a specific strategy that you're going to need to do. You're going to need to split this into two pieces. Notice I'm not integrating yet. All I'm going to do is do x squared over x plus 1 over x. Basically take each part and put it over that denominator to split it into two pieces, dx. Now let's simplify it one more step. This is still the integral from 1 to 2. X squared over x can be simplified down to x. 1 over x I'll just leave alone. And now remember, after you've done this, I still haven't integrated. Let's integrate now. The integral of x is x squared over 2. The integral of 1 over x is the natural log of the absolute value of x. And this is going to be evaluated from 1 to 2. When I plug in 2, I get 2 squared over 2 plus the natural log of, I'm just going to go ahead and put 2 in, I don't need the absolute value, minus 1 squared over 2 plus the natural log of 1. If I simplify this, I get 2 plus the natural log of 2 and 1/2, but then the natural log of 1 is just 0, so that doesn't give me much else. I get 3/2 plus the natural log of 2. Now this last slide, I'm just showing it to you as a quick idea of what you could do as an interpretation of the integral. The net change theorem simply says, if you integrate the derivative on a definite integral, you get a difference in function values. This is the total change in the function value, f of b minus f of a. And f prime of x is the rate of change. So what's kind of nice is if you integrate the rate of change on an interval, you get the total change in that interval. Very handy application. Tons of examples where it comes into play. And so if you run into those in, say, a business class, that's a good place to see them. And other examples too.